Welcome back to part 5 of our Zero to Hero Explainer series. Today is the day we finally stop talking theory and get our hands dirty with a real concrete integration blueprint for mixed vendor AMR fleets. If you've been following along, you know exactly what the stakes are. Facilities are sick and tired of vendor lock-in and those isolated islands of automation. You want the freedom to choose a massive heavy-duty tugger from one manufacturer and a lightning-fast picking robot from another, all running perfectly on the exact same floor. Well, today, we're going to map out exactly how you build that.
All right, let's jump right into this builder's blueprint. Here is our game plan for today. First, we'll cover the fact sheet declaration. Then, we'll tackle traffic control and deadlocks. After that, we'll look at the fleet system architecture, do a quick MassRobotics comparison, and finish up with a concrete integration roadmap for your facility. Let's get to it.
Step 1. The fact sheet. Declaring vehicle capabilities.
You can't possibly control a robot until you know exactly what it can do, right? And that brings us to the very first and honestly most critical handshake of the VDA 5050 standard. When a robot boots up and comes online, it absolutely must send its fact sheet. Think of this as a one-time boot declaration that tells the master control everything, from its physical dimensions and the loads it can carry to its onboard software versions. The whole point here is network efficiency. We have to ensure that static information, stuff that doesn't change while the robot is driving, doesn't clog up your network with every single high-frequency state message. The master control learns who the robot is once and remembers it.
And it's actually pretty brilliant how this declaration is structured. It's organized into standardized property clusters. Take the physical parameters. That covers your maximum speeds, width, and length. That is totally crucial for safety and making sure robots don't bump into things. Then look at protocol limits. This one's super interesting because it literally caps the maximum MQTT message length, actively preventing buffer overflows on vehicles with highly constrained onboard controllers. By clustering this data, the master control perfectly and safely understands its asset from the very millisecond it connects.
Moving right along to Step 2, Traffic Control and Deadlocks, Managing the Floor.
Okay, so the master brain knows what the robots can do. Now we've got to actually manage their movement so these independent machines don't literally crash into each other. To handle this multi-vendor traffic, VDA 5050 dynamically partitions paths into two key concepts. First, you've got the base. This is the green-lit release ground that a robot is completely cleared to safely drive on right now. Second, there's the horizon. These are the upcoming path segments that the master control is deliberately withholding. It's kind of like a smart train signal system. The master control keeps dynamic command over the bottlenecks and narrow aisles, only giving out resources when they are completely free.
But, things don't always go perfectly to plan. What happens when things go wrong? Despite our absolute best base and horizon planning, we have to prepare for the swap deadlock. This happens when two completely independent robots end up standing on the very nodes each other needs to move forward. They are fiercely contesting the exact ground beneath them.
So how does a weight die sequence actually fix this? Let's say two trucks contest the ground, and the rule dictates the youngest truck has to yield. Here's the catch, and it's a bit like two stubborn people refusing to back up in a narrow grocery store aisle. The yielding vehicle cannot magically free the floor underneath itself. VDA 5050 strictly does not let a release node be taken back. The yielding truck keeps the node it stands on. It has to, which means this weight die cycle literally cannot resolve itself locally. The central master control system has to step in, figure out the mess, and actively reroute them.
That brings us to Step 3, Fleet Manager System Architecture, the central brain.
Because resolving those complex deadlocks we just talked about takes some serious server-side logic. This core concept perfectly highlights VDA 5050's biggest assumption: absolute, centralized, top-down authority. The master control assumes it has complete visibility to manage all routing and coordination. Now, on paper, that sounds fantastic. But in the real world, when you're dealing with a proprietary black box legacy system that's already running your warehouse floor, that absolute authority can be a massive headache. So, to get around that headache, systems engineers use three distinct patterns to bridge legacy systems into this standard. Number one is the plan executor. This is where you actually adapt the legacy software to be the direct VDA 5050 master. Number two is the plan server, where your legacy system translates its commands through a shared middleware broker, which is awesome if you already use middleware for manual workstations. And finally, number three, read-only integration. This is super low risk. Your legacy system simply monitors the VDA state telemetry to see where the other robots are, adjusting its own routes to avoid those swap deadlocks without giving up primary control.
Moving to Step 4, VDA 5050 versus MassRobotics, the broader ecosystem.
Before we finalize any deployment, we really need to zoom out and look at the broader standards ecosystem. There's a fundamental architectural contrast between VDA 5050 and the MassRobotics standard. VDA 5050 is basically a top-down orchestra conductor, giving out precise, centralized routing commands. MassRobotics, though, it's all about peer-to-peer coexistence. It completely bypasses command structures and just focuses on having robots broadcast their location, speed, and destination so they can just be better teammates on the floor.
When you break down the specific dimensions, it becomes super clear. Notice how MassRobotics is totally map agnostic and has literally zero native support for task dispatching. VDA 5050, on the flip side, needs specific maps, like the layout interchange format, and uses native graph commands to move robots. But here's the real aha moment. They are not competitors. No way. A single AMR could absolutely use VDA 5050 to get transport orders from the main fleet manager, while at the exact same time, broadcasting its location to a cleaning robot via MassRobotics. They are incredibly complementary.
And finally, step 5, your concrete integration roadmap, rolling it out.
So, armed with all this knowledge about fact sheets, traffic deadlocks, and architecture, let's build a concrete roadmap for your facility. Let's be real, achieving true interoperability is not just a simple plug-and-play software update. Step 1 is a rigorous site assessment. You have to map out your workflows and find the absolute best fit robots for the job. Step 2 is the turnkey deployment, where you configure your broker and actually integrate that legacy system. And the final step? Unified fleet support. You bring all that complex data into a single, multi-vendor dashboard so you can control any robot, regardless of the brand, from one screen.
As we wrap up this Zero to Hero capstone explainer, I want to leave you with one final thought about the future of your facility. The tools are here. Open standards like VDA 5050 are ready to go right now. The days of vendor lock-in are officially numbered. So, the question is, will you stay restricted to a single manufacturer's ecosystem, completely locked in? Or will you take the leap, leverage these open standards, and build a truly optimized mixed-vendor robotic workforce? Thanks so much for learning with me today, and I highly encourage you to dive into those specifications and start planning your interoperable future.